In Module 6, Lesson 10, we'll describe distributions using the mean and the mean absolute deviation. Recall in Lesson 9, Sabina developed the mean absolute deviation as a number that measures variability in a data distribution. Using the mean and the mean absolute deviation with a dot plot allows you to describe the center, the spread, and the shape of a data distribution. For example, suppose that data on the number of pets for 10 students is shown in the dot plot below. There are several ways to describe the data distribution. The mean number of pets each student has is 3, which is a measure of the center. There is variability in the number of pets the students have, which is an average of 2.2 pets from the mean. And the shape of the distribution is heavy on the left and it thins out to the right. So we would say that it is skewed right. Suppose that the weights of 7 middle school students' backpacks are given below. We'll fill in the following table and then draw a dot plot for the data and calculate the mean and the mean absolute deviation. First, since all of the backpacks have exactly the same weight, we could add them all up, 1, 2, 3, 4, 5, 6, 7 times 18, and then divide by 7, but we would find that we get 18 as the mean because there is no variability. So our deviations for each of them are 0, and the absolute value of 0 is 0. So the rest of our table is going to be filled with zeros. So if we describe the distribution of the weights of those backpacks by discussing the center, spread, and shape, we would say the mean, which is the center, is 18 pounds. There is no variability, and all of the data is centered. Now let's suppose that the weight of Elisha's backpack is 17 pounds rather than 18. And we'll draw a dot plot for that new distribution. Without doing any calculation, how is the mean affected by that lighter weight? Would the new mean be the same, smaller, or larger? So since that new value is less than our mean, the mean will be smaller without doing any calculation. How is the mean absolute deviation affected by the lighter weight? Would the new mean absolute deviation be the same, smaller, or larger? So remember, the mean absolute deviation is an absolute value. It will never be negative. And remember that our last mean absolute deviation was 0. So our new mean absolute deviation will be larger or greater than 0. Suppose that in addition to Elisha's backpack weight having changed from 18 to 17, Fred's backpack weight changed from 18 to 19 pounds. We'll draw a dot plot for that new distribution as well. So without doing any calculation, what would be the value of the new mean compared to the original mean? Well, if we have one value that is 1 less than the mean and one value that is 1 greater than the mean, those two will even each other out. They'll cancel each other. So the mean will be the same. Without doing any calculation, would the mean absolute deviation for the new distribution be the same, smaller, or larger than the original mean absolute deviation? Well, there is a deviation here. Two values are 1 away from the mean. So it will be greater than the original, which remember was 0, because there is variability in the data. Without doing any calculation, how would the mean absolute deviation for the new distribution compare to the one in exercise 2? Well, there is more variability because there are 2 pieces of data that are some distance away from the mean. So the MAD for this distribution will be greater. Now, let's suppose that 7 second graders' backpack weights were as follows in the table, all 5. How is the distribution of backpack weights for the second graders similar to the original distribution for 6th graders? There's no variability. So the mean absolute deviation is 0. And the dot plots would look the same too, except of course for the number that's below that set of dots. How are the distributions different? The actual means are different. One mean is 18 and the other is 5. Decision-making by comparing distributions is an important function of statistics. Recall that Robert is trying to decide whether to move to New York City or to San Francisco based on temperature. Comparing the center, spread, and shape for the 2 temperature distributions could help him decide. From the dot plots, Robert saw that monthly temperatures in New York City were spread fairly evenly from around 40 degrees to the 80s, but in San Francisco, the monthly temperatures did not vary as much. He was surprised that the mean temperature was about the same for both cities. The mean absolute deviation of 14 degrees for New York City told him that, on average, a month's temperature was 14 degrees above or below 63 degrees. That's a lot of variability, which was consistent with the dot plot. On the other hand, the mean absolute deviation for San Francisco told him that San Francisco's monthly temperatures differ, on average, only 3.5 degrees from the mean of 64 degrees. So the mean doesn't help Robert very much in making a decision, but the mean absolute deviation and dot plot are helpful. Which city should he choose if he loves hot weather and really dislikes cold weather? Well, I would say obviously you should choose San Francisco, because New York City does go into colder temperatures for a number of months out of the year. Robert wants to compare temperatures for cities B and C. We're going to draw a dot plot of the monthly temperatures for each of the cities. And then we'll verify that the mean monthly temperature for each distribution is 63 degrees. So our dot plots show city B and city C. And we can see clearly that city C has a little more variability than city B does, even though we want to be careful when we look at dot plots that we're looking at our scale across the bottom of our number line to make sure that we are actually comparing the right values. Because if you'll notice, city C's dot plot is starting at 48, and there's a temperature slightly below that, and it goes up to 84. But city B's dot plot is starting at 30 and going to 90. So we want to be careful that we think and really read everything we have there. Next, we'll verify that the mean monthly temperature for each distribution is 63 degrees. In order to verify that, what we're going to do is add all of the temperatures for a particular city and then divide by 12, which is the number of temperatures we have in the table. To verify the 63 degrees, we could look at city B and the dot plot for city B. Notice we have a number of values at 63. We have 3 that are 10 degrees less, and 3 that are 10 degrees more, so they would cancel each other. And we have 1 each that are, it would appear to be 5 less and 5 more, so they also would cancel each other, making a mean of 63. And then we could do the same with these values in city C. If this is 63 right here, 2 that are off this way. And it's a little tough when you have a dot plot that doesn't give you exact values, but what we're looking to do is to find that if we add the sum of their deviations, we should get 0. The mean absolute deviation for each of the cities, remember we have a table, is 5.3 degrees for city B, which means on average a month's temperature differs from 63 degrees by 5.3 degrees. And for city C, it is 10.2 degrees, which means on average a month's temperature differs from 63 degrees by 10.2 degrees. Remember, we do that by finding the absolute value of the differences. So we would do, for example, in city C, 54 minus 63, which will give us -9, and then the absolute value is 9. 44 minus 63, 54 minus 63, 61 minus 63, and so on. And then we would have all of these 12 values that would add up and divide by 12. And that's what gives us our mean absolute deviation of 10.2 or 5.3. How would you describe the differences in the shapes of the monthly temperature distributions of the two cities? Well, in city B, the temperatures are really evenly spread away from the mean of 63. But in city C, there is quite a bit of variability with a concentration of some data to the left, and then it appears to be rather skewed right because it spreads so much further to the right. Suppose that Robert had to decide between cities D, E, and F. We'll draw dot plots for the distribution. So as we look at the dot plots for the three cities, we can see that city D is spread out quite a bit more, and city E has a lot more data to the left, while city F has a lot more data to the right, suggesting that city F is warmer most of the year, where city E is cooler most of the year. And city D has a lot of variability. It is not cold nor hot all year long. Next, we're asked to interpret the mean absolute deviation for the distributions. Now, in our table, the mean absolute deviations are given, and they are exactly the same as are the means. So if they are all the same, Robert's going to need to look at the shapes of the distributions to help him make a decision, not just the mean absolute deviation. And when Robert tries to decide which city he should move to, he'll need to look at things like if he wants to have a variability in the seasons. Does he want to have all 4 seasons? Or does he want it to be warmer more times out of the year, or not too warm? And everyone has their own personal preference, but knowing all of that information will help Robert to make the decision. A data distribution can be described in terms of its center, that's the mean, its spread, which is determined by the mean absolute deviation, and its shape, which will be determined by the dot plot.